Pomeriggio. Because Buonasera is night.
At the dinner.
Yes. Pomeriggio. Okay, I mean sometimes, for example, during 4 p.m. Somebody say usual. But somebody say pomeriggio.
Okay. Buonasera. Okay, also remote. Yeah, sometimes happen. Also in Italian sentence say
It's a mistake.
yeah, it's a common mistake.
Now is 1 after 30. So going on or pomeriggio.
You can see buongiorno is like have a nice day. Buon pomeriggio è good afternoon.
No.
Also buongiorno, you can use buongiorno.
Ciao. efficienza. Grazie. Allora.
Posso firmarti adesso che dopo devo scappare in velocità? Ehi, anche tu vero devi scappare. Sì, veramente. Anche perché arrivare dall'altra parte del mare mi dice che addirittura.
Sei vicino?
No, in macchina.
Sei in macchina? Minuto ancora. Vai pure. Sì, vabbè, dai, ti presento un attimo. Ok, good evening. So, good afternoon, good evening, it's the same.
Io non può esagerare, sono stanchi, ma...
Good morning. Okay, today we have two speakers for our journal club. So I introduce the first presentation about galaxies, and it's to you.
Hello everybody. I choose to present this paper entitled Connected Traces of Galaxy Evolution, the Missing Core Mass Morphological File Structure Relation by Bonfini et al. I structured this presentation in 5 principal sections. We have the introduction, some consideration about time scales and measurements, and then results and conclusion.
C'è anche il microfono.
Non troppo vicino, perché non sentono streaming.
Deep exposure imaging of early type galaxies are revealing second order characteristics of this object, from which one can obtain precious information about the processes that lead to their formation. And in a widely supported scenario, the elliptical galaxies are the end products of violent galaxy interaction, and also this interaction could produce some features such as the fine structures and the depleted stellar cores. These structures have been studied in this paper, and in particular the authors first focused on the fine structure parameter sigma, defined by Schweitzer et al. In the 1990. This sigma parameter measured the strength and or the numbers of morphological structures that are expected to fade out as the gravitational potential relaxes. Here an example of NGC 3640, which have a high value of these sigma parameters. Another parameter to measure the fine structure is the tidal ones, And this was defined by Tal et al. In 2009, and it represents simplified statistics based on some on the measure or some image, the structure that can be put in evidence from images derived from the residual images after subtracting a symmetric galaxy model. That means that you can see dishomogeneities in general or asymmetries and distortion, not only the tidal tails. And here we have an example of an NGC 4261 that have a very small value of the tidal parameter. After this, in addition to the fine structure, the authors looked for the luminous looked for core profile in luminous Early-type galaxies, because from this kind of profile one can deduce. One can obtain the mass deficit in the central region of these galaxies. I show you here an example of the surface brightness profile. We have in green the SRC extrapolation from the outer part of radial profile, and in red the red line is the coarse-SRC profile, that is the observed one. Between the difference of these two profiles, one can derive the missing light and so quantify the mass deficit. The depleted stellar cores are thought to be linked to the dry merger through three-body interaction between stars and supermassive black holes, binary supermassive black holes. The stars get energy from the interaction, and they are ejected from the central part of the newly formed galaxy, so a core could be created. In order to verify this hypothesis of the formation of the depleted stellar cores, the authors did some timescale consideration about the two processes, the two principal processes involved in these scenarios. The first one is the time scale for the supermassive black hole binary to coalesce, and the second one is the fading out of the fine structure. For the coalescing of the supermassive black hole binary, for example, Khan et al. Did some simulation, and they found that this process could last up to 3 gigayears, but if we consider the scoring phase alone, it could last 1 gigayear. So in general, we can say that for dry mergers, we have a time scale of few gigayear. For what is concerned the fading out of fine structures, this is much more difficult to estimate simulation-wise, because it requires to reproduce a great variety of features, and observational-wise because of the low surface brightness of the structures compared to the main body galaxy. But recent works have put an upper limit for the fading out of the fine structures up to 4 gigayear. So the Bonfini et al. Concluded that the fine structure could coexist with the supermassive black hole binaries, at least for and could coexist and act in parallel, at least for the few gigayear of the galaxy formation.
Which part of the galaxy are we talking about? Is it the central parts or the periphery or in between?
We are considering only the central part of the galaxy, yeah. But these are very massive and luminous galaxies. They used, the authors used a sample of nearby helicopter galaxies for which they could retrieve literature values for both fine structure parameters and stellar mass deficit. For the fine structure parameters, in this specific case, for the sigma parameters, they used the sample by Schweitzer et al. And to find, they want to find other, for the same galaxies, that have been observed and for which they could find a core profile, course axis profile. So they cross-correlated the Schweitzer sample with that of Dulu and Graham 2014 and Richings et al. 2011. So they found 19 galaxies in common, 5 having sigma parameter equal to 0 and 14 having sigma parameter greater than 0. They did the same cross-correlation with the Richings and Dullo, but for the sample of Tal et al. 2009, for which we have the tidal parameter. They found 8 galaxies in common, 7 having tidal parameter greater than 0 and 1 having tidal parameter equal to 0. Then they calculated mass deficit and plotted the two fine structure parameters against the mass deficit normalized by the spheroid mass. As you can see in the both panel, the points follow a straight line. They also limited the range of best fitting using the bootstrapping method to avoid that the highest value of sigma parameter could influence too much the linear fit. And they found an anti-correlation between the sigma or tidal parameter and the mass deficit. Moreover, for the sigma parameter, they found they added 2 more galaxies that are classified as coreless galaxies, but these are expected to develop a core, so they put them at an arbitrary small value of mass deficit. In this way, they drawn an evolutionary track of the evolution of this kind of galaxies. We start from the galaxy start from a low mass deficit, going diagonally until they then stops and go down after 1 gigayear, stops and go down to complete the fading out of the fine structure. To conclude, the authors found that the excavation of the depleted stellar cores and disappearance of the fine structures features occurs in almost in parallel, and that the time scale of this process, the core excavation and the relaxation of the gravitational potential is about 1 gigayear or more. But the most important conclusion is that they found an observational evidence of an anti-correlation between the prominence of fine structures and the mass deficit, the amount of mass that have been removed from the core. All these results support the supermassive black hole scoring as the main channel for the formation of the depleted stellar cores. That's all. Thank you.
Okay, thank you, Michela. Questions?
I have a rather technical, 2 types of technical comments. So one is about the English, forgive me again. I noticed you say parameter, I've never heard it. I think you should say parameter.
parameter. Okay,
Yeah,
thank you.
and where are the words like scenario?
Scenario.
And scenario.
Scenario. Okay, thank
Others
you.
I don't remember. And then there is another thing. It's a mistake in talking that they also make, especially when I don't feel very confident. We tend, I think it's probably very Italian, but we tend to go like
yeah, I know.
for a sentence, and that's very disturbing for the audience. So I'm trying to wean myself out of it, and I think you should do the same.
Thank you.
It's my suggestion because it's quite distracting.
Other questions?
Can you describe a bit more explicitly what goes into the evaluation of the fine structure, the degree of fine structure?
Okay.
Because if I look at this is why I asked before which region of the galaxy we are not talking about. I see a lot of shells, but
Yeah.
this is not the region that the fine structure is measured.
No,
right?
okay.
This is much more out.
No, I thought that was about the course, the depleted stellar course in particular.
Yes.
No, these involve all the galaxy. So it's hard
what
to
they are relating is something that concerns the whole galaxy.
the whole galaxy. So that could be the remnants of an interaction.
Yeah.
So it could be something like shell, but shells also involved a great amount of gas. They they were concentrated on dry merger in
Yes,
particular.
but other lines of reasoning would attribute those ripples that you see there to accretion of satellites which get disrupted. So
Okay.
I don't see how strong the conclusion about the connection between the black hole, which is in the center, and the overall appearance of the galaxy to a large extent, how strong this conclusion.
Okay, because they did some discussion about the supermassive black hole scoring and also alternative scenario that could be AGN feedback and core excavation by infalling and captured perturber. So what did they say is that AGN feedback have a smaller temporal scale, and also the outflows is impulsive, so they could create a core of arbitrary size, and also the AGN feedback requires a larger amount of gas. So they excluded this possibility. The other one is that that one of core excavation by infalling or by satellite, but they say that it's a stochastic event that could not reproduce that trend because larger core require larger satellite, and larger satellite could reproduce larger fine structures. So if you should have a larger satellite, you could find a galaxies to a high value of the sigma parameter, or the tidal parameter, but also with a high mass deficit. So they excluded this scenario.
Okay, I'm sorry to interrupt, but we are running out of time, so thank you very much, Michela. And Chiavetta l'hai presa?
Sì, l'ho presa.
Please, come. Okay, so our second speaker for today, Song Peng Pei, who's talking about X-ray sources. Please.
Okay, good afternoon. Today I would like to present this research, the X-ray eclipse. The X-ray eclipse geometry of super soft X-ray source called 87. Compact binary super soft X-ray sources are systems in which a compact object, often a white dwarf, accretes light from its companion and becomes very luminous up to a unit luminosity. if there is a white dwarf, the luminosity is due to the thermonuclear burning of hydrogen or helium. The dynamical instability mass transfer model is often used to explain the high mass accretion rates in CBSS. For this model, in the CBSS, the donor star is more massive. This would lead to a decrease in the orbital separation of the system, shrinking the Roche of the lobe, Roche lobe of the accreting component, thus forcing more matter to flow from the donor to its companion. This star then becomes thermally unstable, and the mass transfer occurs on a Kelvin-Helmholtz timescales. One outcome of the DIMT model is that for this system, there should display a decrease in orbital period as a result of the decrease in orbital separation. Cal 87 is an eclipsing CBSS in the larger Magellanic Cloud with an orbital period 10.6 hours. All visual inferred an orbital period increase of, so it does not fit the DIMT model. The motivation of this work is to analyze XMM Newton observations of Cal 87 with the aid of eclipse mapping method, map and characterize the X-ray accretion structures of the system. They use the eclipse mapping method to study the geometry of the eclipse of Cal 87. With this method, works by solving an indirect imaging inversion problem to provide a surface brightness map that best fits the eclipse. It assumes that all the changes in flux are caused only by the eclipse of a flat two-dimensional surface plus an eclipsed component that does not vary in phase. XMM Newton carries three types of instrument. First type instrument, EPIC, European full-time imaging camera. It has 3 CCD cameras for X-ray imaging and moderate resolution spectroscopy. The second type instrument, LGS, reflection grating spectrometer. It has 2 spectrometers for high-resolution X-ray spectroscopy. The third type instrument, OM, optical monitor. It is used for optical and UV imaging. The soft and hard X-ray bands eclipse mapping results for Cal 87. In the left panels, we can see the red dots show the light curves of Cal 87. The solid lines show the fitting results. The horizontal dotted lines show the an eclipse component. In the middle, the grayscale map at the center shows the surface brightness distribution in a logarithmic grayscale. The solid lines show shows the Roche lobe of the accreting component. The dashed lines shows the ballistic trajectory. The white dotted lines show the circular radius. In the center, the cross marks the center of the disk. And the arrow shows the uneclipsed shows the asymmetric feature. The right panel shows the radial brightness distribution for each map. For the soft X-ray band, the brightness is flat at the center and it fades quickly. For the radius larger than 0.5 LA1, there the LA1 is the distance from the white dwarf to in the Lagrangian point. On the other hand, for the hard X-ray band, it has a bright feature at the center and steadily fades for outer region. There is a feature that shows there is a feature at the edge of the disk for the hard X-ray band, and this feature is likely due to a bright spot. High resolution X-ray spectra of Cal 87. The figure in the left, the black lines shows the spectra for the whole observation. The red lines show the spectra during eclipse, and the blue lines show the spectra out of eclipse. In the right pan figure, the spectra are shown as a function of time with respect to the light curve on the left, and the eclipses are marked by lines flagged AB and CD. The right panels shows the oxygen 8 line alpha line of alpha line. On the top, the spectra are shown integrated over time for the whole observation. The hardest ratio got from soft and hard X-ray light curves show that the source is hardest during eclipse, and we can see the intensity of emission lines are not emission lines don't depend on the eclipse, so the changes are more likely dominated by the incantium. Together, these features can support the wind the wind-driven mass transfer model. For this model, the strong wind could be induced from the if the donor star is more if the donor star is integrated by the soft X-rays from its companion, and at the same time the mass could be transferred from the less massive to the more massive component. Conclusions. The surface brightness distribution shows an extended and symmetric emission, and the feature is revealed from the hardest X-rays that is likely due to a bright spot. There is no clearly change of the emission even during eclipse. The continuum emission dominates the decrease in flux during eclipse. The results support that the wind-driven mass transfer scenario is running in Cal 87, and with the data of XMM Newton, they also find an orbital period increase. That's all. Thank you.
Questions? No? Okay.
Just one question. How can it be that the lines do not change during the eclipse? Do they come from the... So where do these lines originate?
Yeah, we can see the
Yes, I know, I had seen it already on the data, but
yeah.
I thought that part of the accretive material would also be eclipsed.
But the results they show in this picture,
So in other words, is it possible that the emission lines originate in a material that is enclosing the whole system, so that it doesn't vary with the phase of the binary?
Yes. I think maybe, but this results shows the emission line doesn't change during eclipse.
Yeah, it's in an outer wing.
In an outer ring, that
Wing,
is external,
yeah.
a wing that is
Because
external to the two components.
Yeah.
But it must be thick to make the lines visible also. Cannot be too much
Yeah.
low density because otherwise
Right.
it will be
Yeah. It should be very exact.
Okay. Thank you.
No questions? No? Okay, thank you very much.
Thank you.